Welcome. My name is Paul de Vrieze. I would like to take you through our paper on predictive maintenance for flexible manufacturing. But first I would like to acknowledge my colleagues Lai Xu, Yue Bai, but especially Go Sang, who has been primarily working on this research in the context of the first project. The research I present is done in the context of Industry 4.0, utilizing emerging digital technologies in a manufacturing context. This not only in a supportive role, but also a transformative one, including supporting collaborative manufacturing processes across multiple organizations. One important aspect of manufacturing operation is that of maintenance. All machinery needs maintenance, but it also comes with costs, both indirect costs as well as costs of lost productivity. If it is possible to better plan maintenance, the costs can be reduced. This better planning requires taking information from multiple sources to predict the machine condition. In our paper, we thus address two questions. The first question is how we can use the FIWARE framework to support predictive maintenance. The second, related question is how we can then use a data-driven approach using a short-term memory network model to model machine condition and remaining useful life. In the answer to the two research questions, there exist two key challenges in predictive maintenance. First, how do we manage the complexity and needed capacity for big data in a context with dynamic, complex associations? And second, how to provide the prediction in a way that flexibly and interoperably integrates different systems and components. Our answer to the question of integrating predictive maintenance into FIWARE while addressing the complexity, flexibility and interoperability challenges is a 4-layer architecture consisting of, from bottom to top, a resource layer, a middleware layer, a process layer and an application layer. The resource layer on the bottom allows for data from the shop floor from machines as well as other sensors to be gathered. On the middleware layer, the context broker represents the core middleware in a publish and subscribe manner that accommodates the interaction of all kinds of components in the system, including using data adapters to provide relevant data to the big data processing engines in the process layer. The process layer performs the actual modeling that is essential for predictive maintenance using specialistic data storage such as Hadoop distributed file system. Finally, the application layer provides access to the overall system, including the predictive maintenance components. This could, for example, take the shape of a dashboard for monitoring predictive maintenance and maintenance scheduling purposes. On the second research question, predictive maintenance, we have used the long short-term memory network approach. This particular recurrent neural network overcomes the complexity in memory problems and is thus quite suitable for the problem of predictive maintenance. As shown here, the model creation starts with data processing, first collecting the data from various sources and then preparation, including normalization. Next, this prepared data is used for model training, including the initial setup of the model. Finally, the evaluation step uses a testing dataset to evaluate the model quality. If successful, the model is then ready for use. To evaluate the approach, we have used a case study. This case study consists of various equipment, including trolleys, robots and CNC machines. Data is collected from these different machines as well as other information systems such as ERP, MES, etc. In a case such as our case study, data is collected by the system on all machines. Here you can see a sample data model for some machines. This model can be extended for specific machines when such data is needed, for example, for prediction accuracy. In the implementation of the actual case, we have made concrete choices for the components used, for example using the Orion context broker and Cosmos data analysis system. For our case, we prepared the data based upon an initial sample. A graphic representation of this data is presented here. It is clear that worn and unworn machines have different properties and as such wear should be able to be predicted. After our preliminary modeling, The prediction results show that in this preliminary work there is a good quality of prediction, but we will be doing further work to further analyze this in more detail with a more complete dataset. To conclude, we have proposed a modular framework for predictive maintenance using FIWARE. This framework can handle the requirements of Industry 4.0 and enables advanced analytics such as LSTM networks. To evaluate the framework, we showed the effectiveness of the approach using a flexible manufacturing case. Finally, I would like to thank you for your attention. Please contact us with any questions you have.